Hello, we present our project, Real Environment Simulation Jungle. Our team are conformed by Amaury Blanco, Alexis España, and me, Marco Martinez. The goal of our project is create a scene with a realistic jungle simulation. Have a camera to navigate around the scene. In the camera method, it exists a method to calculate collision between the camera and the objects. The camera navigation are made by Amaury Blanco. The method to load the 3D objects are made by Alexis España, and me create objects in Maya and 3D Max. In order to create the 3D models, we first load the 3D model in Maya. These models are created by Sanchi Espep and has the royalty-free license. After that, reduce the topology at 50%. And then reduce. Okay, and this means the quads are divided by 2 and then triangulate the mesh. Steps are necessary because the original model has a lot of faces and vertices in quads, and OpenGL demands a lot of memory with the original topology. That means a lot of time on charging the scene and limited movement of the camera because the program is rendering real-time topologies. This includes a texture. For the texture, it is only necessary to convert the image in BMP or Photoshop. This step is necessary to load the image in the method created in OpenGL. My teammate Alexis España explained the method to load the 3D objects in OpenGL, and after that Amaury Blanco explained the method to create the camera and the navigation in the scene.
So, creating objects in OpenGL is a hard task, and we prefer to do this using modeling tools as Maya and Blender, and export them and then load the models in OpenGL using a method. I will explain this method. Is to codes these two class I don't know scripts with help with help, and Sofia Bankov was the classmate that helped us to implement these two scripts. And well, let's explain this. Where we implement the function of the load object, we have a constant chart of the paths, the vectors, the 3 vectors mentioned before, and we need 3 vectors, temporal vectors, and this in another vector to store information about the faces. Well, the first thing we do is open the file using the path. If the file is null, that means that we can't, that wasn't possible to open the file. So we print a notification. So in this cycle, in this while, what we do is to read the information of the file. So we have a line header that where we will store that is used to read each line of the file, and we store this in res. If res returns, if scanf returns end of line, that means that the file doesn't have more information and we need to break the reading while. So if we read if the line header that we read is a B, that means that we are reading information of the vertex. So we read the float values and store them, and then we do a pushback to the temporal vector, and we do this with the information about the BT, that are the texture information, also with the normals. And if we are reading a F, that means that it's information about the vertices that are using each faces. So we need this to store the information about what vertices are using the faces, each face, and then we store that information in the main vectors. So in the main script, we have the methods to load, to display the objects that we have loaded using the OpenGL loader CPP and the OpenGL loader HPP. So we need the vectors for the vertices, U, and the texture and normals for each object that we are going to load. We need for the rhino, for the lion, elephant, giraffe, and tiger, and so on. So in our init method, where is our init? So we need a load method in which we just call the method loadout with the path and the vertices, with the vectors, the vectors where we want to store the information, and this method is called in the init here in this line. After we have loaded the information about each object, then we display in the method display. In the method display, we just call the blind texture to apply the texture about our object, that this part was explained by Amaury, and then we display the information about each object, for example the rhino, the lion, and so on. And we have a display for each object, each animal or each plant. Here we have a display, and consists just to apply a scale, and using the primitive GL triangles we do a for to record each vertex and just put the coordinates about the texture and the coordinates about the normals, and the information about the normals, and the coordinates about each vertex. In order to calculate collisions between our objects and our camera, we have two different types of colliders. The first one is a sphere collider, and the second one is a box collider. Our camera is using a sphere collider, and the collision between our camera and an object that is using a sphere collider is very simple. We need to know the values of the center of this sphere, the camera sphere collider, and the center of the collider of the object. So we calculate the distance between these 2 points, and if the distance is lower than the sum of the radius of the collider and the camera collider, that means there exists a collision between them. So it's very simple. And for some objects it is necessary to use a box collider, that they are very a little complex than more complex than other ones. So for a box collider we need to know also the center of this box collider. We need to know this value of, I will call this W1, and this value also, and I will call this W2. And this is because box collider doesn't is not necessarily a cube, and it could be a rectangular prism, and we need to know the height also. So to know if there is a collision between a box collider and our camera, we need to know the vector of the movement of our camera. Let's suppose that is moving in this axis, our camera. And what happens with the faces of our collider? How to know in which phase we could be a collision. It is necessary to know the normals of the faces. For example, for this phase, the normal will be in this direction. For this one, this normal will be in this direction. Is in this direction. And for this and the other direction. Finally, in this direction. So, what happens with the movement? If since we know the direction of the camera, of the movement of the camera, we can know with which faces could be a collision. For example, for this face, for the face of here, we can know that couldn't be a direction, since the normal of this face, this normal, and the normal and the vector of the direction of the movement or camera are perpendicular. So it is not necessary to check if could be a collision between them. And the faces where could be exist a collision is this one and this one, since the vectors are parallel between them. This the normal vectors and the movement vector of our camera. So it is necessary to check if there is a collision, and we know this so similar to the as we did with the sphere. We need to know the center of the collider and the center of the camera collider. We then calculate the distance, and if the sum of the center to the W1 of W2 plus the radius of our collider, of the camera collider, if the distance is lower than that sum, that means that there is a collision. Otherwise, there is no collision.
After loading the objects, the next step was loading the textures. For texture mapping, the readBMP file method provided in class was used to map texture for the skybox, the terrain, the animals, and the plants. These objects were loaded with triangles, and their vertex were used to map each texture, using the coordinates for each triangle. Regarding the skybox, a cube map was generated. Using quads, a 3D cube was created for the skybox structure. Its texture is an unfolded box, and its coordinates were calculated between 0 and 1 for S and T values, giving an order for each face of the cube. The camera was put inside the box, so the aspect of being in a big scene could be given. For the camera movement, we used the computer graphics using OpenGL by Francis Hill book to learn how the camera worked, and all the parameters and classes involved were needed in order to move within the scene. Creating provided methods and generating others, the program allows the user to move forward, backwards, slide from left to right, slide from up to down, and rotate from left and right, moving within and outside the skybox and among all the pooled objects.
As you can see, the objects are loaded in the scene, where different animals and plants are generated with their texture. The camera movement allows vertical and horizontal movements, besides rotating in its own axis, from left to right. The user is able to navigate between the scene to have a better perspective of the objects. Besides the terrain, the skybox in the background can be seen, with its corresponding texture giving a jungle environment. The objects were loaded with triangles, and their texture was mapped with their corresponding vertices within the same generating vertex loop when loading the objects, allowing to map the exact position of the texture, giving a real look-alike aspect for each object.